There we go. Sorry, you missed a slide. All right, number two. The next thing we talked about with position was velocity. If the position changes, we can see how fast the position changes, and we get the velocity, and we know that velocity is the change in position over the change in time. We can also measure how quick that angle is changing. So if something is going around in a circle, we can measure the rate of change of the angular position and get angular velocity, which has the exact same equation form. Oops, that's supposed to be theta. Except now we're going to use angular position. So it's delta theta over delta t. What do you think the units will be? Radians per second. Radians per second is the units. Okay, so in this particular case, notice they're using the same sort of diagram. It's just now maybe this point has gone from here over to there. Well, let's see from an angular perspective how much its position has changed. And it's like, well, point the line there and then point the line there. What's that angular difference? How much time did it take? That's an angular velocity. Okay? How many radians for every second does it move? Yes?
Why do we need to know this? Why do we need to know the...
We'll get there. This is all sort of a setup for things that are coming. And we'll get there probably in about 20 minutes. Okay? Yeah.
Sorry, what's the W thing called again?
Omega. Omega is angular velocity. Lowercase curly w. Position, velocity, what was next? Acceleration. If the velocity is changing, we call that acceleration. So yes, we had acceleration was the change in velocity over change in time. So now we're going to have an angular acceleration. Something could be going around in a circle and going faster and faster and faster, right? That's a speeding up. It's just that its angle is speeding up. We're going to use alpha for angular acceleration, and it is the change in angular velocity over the change in time. What do you think the units will be this time? Radians per second squared. Okay, position, velocity, acceleration. Angular versions of all three of those. If you look back through your notes and look at what we did next, and again, this is like sort of big topics that we covered. After we learned about our basic motion quantities, we put all of those together into a type of problem where we listed out the variables and we had 4 equations to choose from. Hopefully you all remember this because you're going to have to do it again really soon, which was called kinematics. It turns out we can do that in a rotational fashion as well. So we're going to have angular or rotational kinematics. And I put both of the words up there because I kind of use them interchangeably. They really mean the same thing. Okay, and you'll see it referred in different ways in different textbooks. So angular or rotational kinematics, we will again have 6 variables. And we're going to do an example of this, which will serve both as a bit of a refresher and something new all at the same time. So previously we had, let's see, x initial and x final, and v initial, v final, acceleration and time, or we had those in the y direction, we have that as well. We're just going to switch all these over into angular versions. So the first one becomes an angular position, so it'll be theta initial, and then an angular position, theta final. This one will be omega initial, that'll be omega final. This one is alpha, and that is time. So it's literally like we're just using a new language, okay? We're just translating from one thing to the other, and it's almost like we took the same things and just made them a little squiggly and blurry, but it's the same idea. positions, velocity, acceleration, time, just in terms of angular quantities. We are going to have the same 4 equations. You just have to make the substitutions. We're going to do an example connecting all this together in just a little bit. I need to give you a little more background information before we can do a problem. Okay? So, yeah, I know it's terribly exciting. People are yelling, they want to get in here and take this class, and alas, we're full, right? All the seats are taken, totally full. So there are connections between these two worlds, between what we learned before, linearly, and what we know now, angular or rotationally. There are 4 different equations that will allow you to convert from one to the other. And you will find that often in a given problem, you can work it 2 different ways. You can use linear motion, or you can use rotational motion, and our example is going to show you how that works. So the first one we have already talked about. S is equal to r theta. Theta is an angular measurement. S is like an actual physical measurement that I can find, a distance along a circle. Okay, S is equal to r theta. And you're going to see a trend here. V is equal to r times omega. So the linear thing equals the radius times the angular thing. And then A is equal to R alpha. And allow me to make one little modification to these 2 equations. I wanted to point out what they looked like first before I got into the details. I'm going to put a little T on both of those to indicate this is specifically tangential velocity, which is just a fancier name for what we already know about. And let me explain in a second. This is tangential acceleration. So circle, and let's say we have an object here, and it's going around the circle this way, which, yes, means it has an angular velocity, okay, as measured from the center of the circle. You could stand at the center of the circle and be like, the object is here, and it's going around this way. It has an angular velocity. But also, at this point, it is moving tangent to the circle. That is the tangential velocity. Those 2 quantities are connected by the radius, okay? So as it moves around the circle, it has a linear velocity that's always tangent to that circle. This tangential acceleration is also tangent to the circle, but it could be in either direction depending on whether it's speeding up or slowing down, okay? But it's just like before. It's going to be along the tangent line to the circle at any point. And then number 4 is kind of off by itself just a little bit. It is the other acceleration we learned about, the centripetal acceleration, a sub c, which we know before was v squared over r. That v is a tangential velocity. It's how fast it's moving tangent to the circle. And now, since we have an equation for tangential velocity, I can plug that in. We'll get a new expression. So r squared omega squared over r. One of the r's cancels, and we're left with r omega squared. And remember that the centripetal acceleration is the thing that makes it turn. It's perpendicular to the velocity, and it's the thing that makes it turn in a circle at all. So let's see. This one makes it speed up or slow down. This one makes it turn. All right? 4 connection equations between the 2. So here in just a few slides, after we do some multiple choice questions, we're going to do an example connecting all of these things together. All right? So a few people writing. I'm being patient-ish. So, next slide. And yay, there we go. Okay? Rabbits. There they are. They look excited. Wow, they really do look excited, don't they? Rabbits. Bonnie and Clyde. Bonnie sits on the outside and Clyde more toward the middle. And they're on a merry-go-round because this happens all the time, right? Rabbits riding a merry-go-round that's rotating in the direction you can see. Here's the problem with this problem. I did this in class one time, and I talked about it for a while, and I was like, I didn't look at the screen. I was just like, rabbits, Bonnie and Clyde, blah, 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 blah. They're riding a merry-go-round, and there's the rabbits, and there's these rabbits, and the rabbits are doing this. And then I turned around, and I was like, there's no rabbits. The rabbits were gone. And I was thinking, I reviewed this problem the night before. There were rabbits in this problem. I know there were rabbits in this problem. Unless I've completely lost it. Have I lost it? What's happening? So I asked the class, and I was like, do you see rabbits? And I go, we don't see any rabbits. Why are you talking about rabbits? Like, because there's supposed to be rabbits in this problem. Thankfully, I went home, I looked at the notes again. The original slide had rabbits. Something in the copy-paste of getting it into the lecture, the rabbits didn't copy. And I was left just looking like a fool. And it was sad. But alas, I wasn't crazy, and I was happy to know that. So there are rabbits here. You see them, yes? Okay, no? Now you're freaking me out. Because it doesn't say rabbits up there anywhere. This says Bonnie and Clyde. Anyway, they're riding this thing around together, okay? What can you say about their angular velocities? Imagine you're standing at the middle, measuring their angle and how fast it's changing. Any thoughts? Would they take a different amount of time to go all the way around? No, right? So if they start here and travel around the circle and get back to the exact same point, they must have the exact same angular velocity, okay? They have the same angular velocity. If I stand here at the middle and watch them, they're always going to have the same angular position from my standpoint, okay? However, they're not necessarily moving at the same speed. If we were to look at their tangential linear velocity, is one of them moving faster? Which one has farther to go?
The one with more radius.
Yeah, the one with more radius, which is Bonnie, right? Bonnie has a bigger circle to travel than Clyde. So if they're going to get back to this same line, Bonnie has to travel faster to get around the circle in time. Okay, so Bonnie has a larger tangential velocity. And you can make that connection by saying Vt is equal to R omega. So this one is the same, but this one is larger. Say for Bonnie. Good? Not too bad, right? Okay. Let's see, this next one we're going to skip. Boom, gone. That was fun. This next one we are going to talk about. And I will have to walk through these two with you. So an object at rest begins to rotate with constant angular acceleration. So if it helps, just imagine a wheel. It's just sitting there, and then for some reason, it starts to spin and spin faster and faster and faster, okay? This object rotates through an angle theta in the time t. So we're saying we maybe start a stopwatch, wait a certain amount of time, and then see how much of an angle it has rotated around, all right? How does that compare to the angle in half the time? The angle in half the time. What we can do is use the first kinematic equation, which you should recognize it just has weird symbols in it now. Okay, it's full of Greek. The same first kinematic equation. Let's just say it starts at zero angle. They told us it starts at rest, so that one's gone. They said that both of them have the same angular acceleration. So now we just want to see what happens to theta if I plug in half the amount of time. Okay, half the amount of time. So let's do that. So if I plug in t over 2 and square that, we're going to have t squared over 4, which means that if I get theta final from t, If I plug in t over 2, I'm going to get theta final over 4. Okay, so it goes a fourth of the angle in half of the time. So your answer there is number 2. Yes? Maybe? Okay, yeah. Somebody likes it. Once again, yeah. All right. Let's see the same problem, but now we're going to say it's rotating with that velocity after time t. How fast was it rotating in half the time? For this one, we're going to use a different equation. We need one that compares the variables that they're talking about in the problem. So again, it starts from rest. The angular acceleration is the same. And you can see now omega final and t are just directly proportional. There's no difference. They're directly proportional instead of being squared. So let's see, if t gives me omega final, t over 2 is going to give me omega final over 2. So it's going to be traveling at half the angular velocity, all right? Questions about those two before we finally get to do an example? I hope the example kind of pulls all these slides together for you. Anybody? Nothing? Okay. Yo-yos. Does anybody play with yo-yos? Does anybody not know what a yo-yo is? You all know what yo-yos are, yes? I feel like there was a time where people just like walked around with yo-yos. It was like a thing. Like, I don't know, like, almost like today we all just walk around with headphones listening to something. It's like then it's like we needed to distract ourselves by playing with a yo-yo. I don't know. That was never me because I could never really get the hang of it. It was like, what's happening here? Like, none of this is working, all right? So in this particular case, we're going to kind of play with a yo-yo by attaching it to a ceiling, which doesn't sound like the proper way to use the yo-yo. We're going to unwind it just a little bit so we can make the attachment, hold it here, and then let it go, okay? So if you think about this, this is going to do two things at the same time. It's going to unwind, right, which means the yo-yo is going to be forced to spin, but also it's going straight down. So it has linear motion at the same time that it has rotational motion. And they're both linked to each other by the string. The string is essentially making the rotation happen. If it wasn't there, it would just fall and go straight, okay? So this one is going to let us use both types of analysis to solve the same problem, linear motion and angular motion. So let's work through these questions and then add to it just a little bit. The first one, A, what is the linear acceleration of the descending yo-yo? The linear acceleration. It's asking us for AT, which we know is equal to R times alpha. And they actually gave us alpha, and they gave us R. So this turned out to be relatively easy. Just make sure that the units are consistent. So if I want AT in meters per second squared, we're going to use 0.031 meters and 0.78 radians per second squared. And you should get a number on one of these slides somewhere, 0.024 meters per second squared. Does anybody see an issue? A problem? Something there that might disturb you a little bit if you think about it too much. Like, no. Gave us two numbers, we punched them in the calculator, and that's the number that came out. Think a little more about it. Units. What about the units? Something didn't quite go right there, did it? We know we should get meters per second squared. We know that's the units of regular acceleration. But you are correct. What do we have here? We put in meters for this one. And we put in radians per second squared for that one. Which means I should get meters times radians per second squared. I can't have acceleration in meters times radians per second squared. That makes no sense. Turns out we didn't make a mistake. The mistake or the issue is that radians are weird. They're just strange. They're like ghost units, if I could be allowed to call them ghost units. Here's the thing about radians. Radians are what we call dimensionless. If you go back all the way to the first lecture we had, we talked about dimensions and dimensional analysis and how things can have dimensions of length or time or mass in this particular course. More to be added later on. Well, if you think about an angle, it's not a length. A length is something physical that I can measure. It's not a time and it's not a mass. It doesn't fit any of the dimensions. Which means it's literally a ghost. It's there when you need it and not there when you don't. Or is that backwards from a ghost? I think ghost would be there when you don't need it. Do you ever need a ghost? Maybe you don't. I don't know. Here's the thing. This radians, we know that acceleration linearly is meters per second squared. So, bye-bye. The radians just drift off into the ether and gone. Okay? If we were going the other direction and trying to get from AT over into alpha, notice what would have happened. We would have meters per second squared, and we would divide by meters, and then I would just have units of 1 over second squared. And I'd be like, but it's angular acceleration. I know I need radians, so we would say, ooh, in comes some radians right when I need them. Okay? I'm sorry. I pointed out because I know it tends to be confusing because you're going to get home and work on homework and you're going to be like, my units aren't working. I don't know what's happening. You just have to accept the fact that radians are a bit of a ghost. All right? It's not really incorrect to say that these units are just 1 over second squared, but putting the radians there tells you a little more information. Okay? So radians are dimensionless. We'll say like a ghost. I would say ghosts are dimensionless. I guess, hey, this whole analogy is kind of working. Why not? Okay? Don't think about it too much and you'll be okay. I don't have a better explanation. I'm sorry. So let's do part B. Part B. Part B says, how long does it take the yo-yo to reach the bottom of the string if it starts from rest with 5.2 centimeters already unwound? So that means in our little diagram over here, this is 5.2 centimeters. And notice it says that the length of the string that's wound is 1.1 meters total. Okay? So how much string is left? Let's find that for starters. How much string remaining? This will help us find how much time it'll take to get rid of all that string, to make it all unwind. So how much string is remaining? I had 1.1 meters and 5.2 centimeters is already gone, so 0.052 meters. Somebody tell me what that is. What is it, 1.048 meters remaining? And then it'll be out of string, and it will have reached the bottom. Okay? Here's the thing about the string in this particular case. It's kind of nice because it's like a physical representation of arc length. As it spins and I take some of the string off, it's like I'm peeling off the edge of the circle. It's almost like I get like a physical measurement of arc length, which is kind of nice. So in other words, as this thing rotates, it's going to rotate through this much arc length before it reaches the bottom. Okay, so that means we can say that this is equal to S. Let's see if we can find out how much angle it's going to rotate around as it gets to the bottom. So S is equal to R theta. So theta is S over R. So that's 1.048 divided by 0.031. You should get 33.8 radians. That's how much rotation it's going to go around before it reaches the bottom. Remember how much is in one rotation? 6.28. Notice it's going to spin around several times before it gets to the bottom. I think this is one of the things that confuses people about theta and angular position, is because it repeats. When I say x is equal to 2, that is one particular place, and it's that place. But when I say theta is, I don't know, 2 radians, right? I could imagine like, okay, we rotate around as 2 radians, it's like right here. Well, I could keep spinning around, and now right here means something else. Or I could spin around 50 times and point to that place, and it means something else. So the same location can indicate multiple angles depending on how many spins you went through to get there, all right? So 33.8 indicates that this is going to rotate several times before it reaches the bottom of the string. This theta final, or this angle rather, is theta final. It's the final angular position of the yo-yo when it gets to the bottom, which means I can start to do something like this. Maybe theta initial was 0, and omega initial is 0, and omega final is something I don't know, and alpha is 0.78 radians per second squared, and the time is something I don't know. And all of a sudden we're starting to do a problem that you should be kind of familiar with, right? List the variables, and then find the question marks. We got 2 positions, 2 velocities, acceleration, and time, all of them angular, except for the time. Angular time. I don't know what that would mean. That sounds strange. Okay? So if I want to find t, we just need to pick the appropriate equation. And we can use the first one, theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. That's 0, that's 0. And you can solve that for time. Time here is going to be 2 theta final over alpha, and take a square root. So that's 2 times 33.8 divided by 0.78. And you get a very depressing number. You're like, how can time be depressing? Oh, it can be, especially when you're playing with a yo-yo that gives you this amount of time. Anybody have it? You may not believe the answer you get. Some of you are writing, some of you are just not calculating. It's impressive. I had someone this morning, the person next to them even handed them a calculator, and they were just like, not gonna do it. I ain't touching your calculator. I'm not calculating anything. It's 8 o'clock in the morning. I don't use calculators before 9. I don't know what was going on. Did you get a number you don't like?
I got 9.3.
9.3. What kind of yo-yo is this? Right? Think about it. The yo-yo is never going to get to the bottom. This is a very slow motion yo-yo, right? These numbers were not chosen very well, I don't think, because I don't think anyone has the patience. Maybe this is why yo-yos kind of went out of fashion. It's just not fast-paced enough. It takes like 18 seconds for one trip down and back. Nobody wants to play with a toy that's slow. So I'm sorry that number doesn't make a whole lot of sense, but you get the idea. 9.3 seconds to reach the bottom of the string. Part C only asks us to find the other question mark. What is the final angular velocity just before it reaches the bottom of the string? How fast is it spinning right when it runs out of string? Well, for that, we can use another equation. Omega final equals omega initial plus alpha times time. That is 0. And now that I have the time, I have lots of time, 9.3 seconds, we can find theta final. Theta final is 0.78 times 9.3, which is 7.3 radians per second. So if 6.28 is one circle, it's spinning a little more than once per second once it reaches the bottom of the string. Who's got questions? I'm not quite done with this problem yet, but I'm done with the angular part of it. That should feel a little familiar, if not like familiar with a dash of new and confusing. Okay, it's not totally new because the problem and the equations are basically the same, but the terminology is definitely different. Anybody? Okay. So let me jump over here to the side where I left a little bit of room. Also, you can see this problem clearly went further. Part D, like there's no part D. There we go, get rid of that. Let's see. Remember we said that it's rotating, but it's also moving in a straight line. That means I can still look at this problem from the standpoint of like, there's an object, and I don't really care that it's spinning, it's going straight down. I can analyze that motion as well. We could do this and say that it maybe starts at 0 and ends up 1.048 meters later. That's how far down it has to travel. And the initial velocity is 0, and the final velocity we don't know. And the acceleration tangential is something we found way back in part A. That was 0.024. It's not falling very fast. It's like nowhere close to free fall. 0.024 is a whole lot less than 9.8, right? So it's just moving down sluggishly, eventually getting to the bottom. And time, we don't know. Notice the 2 question marks are analogous to the 2 question marks we had here. Instead of the angular version, I have the linear version and time. You should be able to work the problem this way using what we had way back in chapter 2 and get the exact same answers. Time should come out to be the same. Vf should be related to omega f by means of that conversion equation we had. V is equal to r times omega. You should be able to convert between the two. So in other words, try this. Compare your answers. All right? You should be able to get the same things. And I just wrote some stuff up there that didn't appear. Go. You can do it. It's still here. Oh, look at that. Fancy. Weird. Come back. You can do it. All is lost. Things are still connected. This is just spinning. Unable to connect. Well, thank you. I know that. Try again. Don't give up. We have too much to learn still. All right. Let's go check the Wi-Fi. It's connected there. Turn it off. Turn it back on. Connect it again. Go back over here. Do the thing. Tap the button. Why? Be good. Okay, class is over. No. Boy, some heads popped up so fast there. That was just stunning. Let me disconnect the Wi-Fi again and give it a second. So how's everybody? You good? Yeah, maybe I turned it back on too fast. You're good? You're fine? I'll tell you what else I'm going to do too. I'll reboot here. Zinga. There we go. And then we wait. We turn that back on. I don't think that's happened all semester. It always just reconnected again. One of you is jamming the signal, aren't you? Uh-huh. It's these goldfish. It's the goldfish, the ghost, you think? Could be. I think it's the goldfish, because I don't think I've seen people eat goldfish in here before. That's the new variable. You're thinking, I eat goldfish every class. I don't know.
Yeah.
You do? Okay. Goldfish are good. Think about it, though, as you bite off their little heads. It's a little disturbing. A little. Think it's going to work this time? You ready? I need all of you sending, like, positive Wi-Fi energy this way, as if that's a thing. Ooh, that's a good sign. Now whoever's out there with the jammer are all like, yay! No, that person is like, yeah, I will do it again. I will make it drop the signal. Now it's a little flashy. That doesn't seem happy. Okay, If anyone starts to feel seizure-y, let me know, and we'll just turn the projector off or something. Yeah, that's a little frightening. So let's see. Try this and compare answers. See, I wrote it there. I promised you. So there is that problem. You can do that both ways. The next thing that's here, we're not doing this one. It doesn't really help anything. Moving on. This screen is blank, so we're not going to do that one. We're not going to do the blank screening. That's kind of useless. Which brings me to something that's going to take a little while to talk about. Okay, it's going to take most of the rest of class. Okay, and that is continuing what we were doing. We did this position. We switched over to angular position. Velocity, we switched over to angular velocity. Acceleration, we switched over to angular acceleration. And then we had basically new kinematics, which was just a rotational version of what we had before, okay? Here's what we're going to do next. We're going to take mass and find a new rotational version. Okay? And it turns out this rotational version of mass, which you see up here, rotational mass, has a name. It's called moment of inertia, which seems to be a bit of a weird name for something, okay? Moment of inertia. You can think of moment of inertia as an analog to mass, except for things that are rotating. So, rotational mass with air quotes. And it's going to take a while to get this idea across. It sounds like, oh, you explained it, you're done. No, I'm sorry, okay? People struggle with this one a little bit, so I want to take a little extra time. Mass, we get the idea. It's like more mass means it's harder to accelerate that object. F equals ma takes more force if something has more mass. In other words, mass, we said, was an object's opposition or resistance to acceleration. The same idea applies here. You can see on the second line, except this is a measure of an object's resistance, not to regular acceleration, but to any changes in its rotational motion. Change in rotational motion is angular acceleration. And look at that. There's a little punctuation that shouldn't be there. Go away. That's irritating. A measure of an object's resistance to angular acceleration. So if I go back and think about the tire that is not here, right? Here it is. Like you could imagine, like, well, how hard is it for me to like rotate this? It's not moving, and now I want to spin it. How hard was that? Okay. Maybe now I decide to replace the tire with, I'm not even sure what. Like 3 of you. I take 3 of you and I'm like, here, sit on this axis. And put 3 of you here, and then I'm like, we're going to spin. And maybe it's a little harder to spin. It's more opposition to being rotated. And then maybe if I swap that out, and instead of like a wheel, maybe I take a wheel that's this big and swap it out for one that's like smaller. And now maybe it's like, ooh, well, that was pretty easy to spin. Like there wasn't much of a wheel there at all. How difficult it is to rotate an object is a measurement of its moment of inertia, its rotational mass. The tricky part about this is it's not mass. It's not just about how much mass is there, but it's about where the mass is located. Okay? So here's the way that I'm going to have to illustrate this. I'm going to take this slide and the next slide, which is completely blank except for a title up there, to go through sort of a series of steps that builds up into explaining what we mean by moment of inertia, okay? It depends on how the mass is distributed throughout the object. So it's not just about how much mass is there, but about where it's located. So let's talk about a couple of different things. First of all, I'm looking for props. No, nothing I like, so I'm just going to go with this. Let's start with the most simple case we can. 1 point mass. Force to move in a circle. I'm going to draw a diagram to show you what I mean. So we're going to say that this is an axis. We'll call it the axis of rotation. So we have moment of inertia and axis of rotation. It sounds like we're using fancy language all of a sudden for some reason. I don't know. Makes me think of Agents of S.H.I.E.L.D. Anybody watch Agents of S.H.I.E.L.D.? Nobody? Nothing? Marvel stuff in general? Okay, but not Agents of S.H.I.E.L.D. Go watch Agents of S.H.I.E.L.D. It's a good time. 6th season to be released next year. But anyway, what movie was he in? I think he was in the Thor movies. Agent Coulson? You know Agent Coulson? Yeah. Well, the people from Thor's planet call him Son of Coal. Coulson, Son of Coal, like that. Cracks me up every time. That's what this makes me think of. Instead of saying rotation axis, axis of rotation. Like, I don't know, it just sounds more fancy. Just laugh and go watch Agents of S.H.I.E.L.D. Not now, lunchtime, right after class, all right? So let's say that out here somewhere is a mass. And it's connected to this axis of rotation a distance r away by what we're going to say is a massless rod. By massless, I just mean that its mass is really, 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 really low compared to the mass itself. Okay, like it doesn't really impact the problem. So imagine that you can reach in and grab this axis of rotation and like turn it. It's like a dial, but it's got this mass out here that's like on the side, so that when I turn it, the mass is like forced to rotate one direction or the other. All right? There's going to be some level of difficulty in doing that. And it depends on a couple of things. It depends on, well, how much mass is here, but also how far away it is. Imagine right now that you grab this and decide to turn it counterclockwise, and it offers some resistance. It's a certain level of difficulty. Just imagine a certain level of difficulty. You got it? You got a level of difficulty in your head? How does that change if all of a sudden, like maybe I decide, nope, sorry, we're changing things. This is really, really long, and I'm going to put the mass way out here. The exact same mass, but now it's on a rod and it's really, really far away. Did it get harder or easier to turn? Seems like it might be harder. If you take it to an extreme, what if now that rod is like 1 kilometer long, right? And now when I turn this, like that mass is way out there and it goes and like moves around this huge massive circle of radius 1 kilometer. You can imagine that me trying to turn this just a little bit, which is going to make that move a lot, is going to be really, really hard, okay? So taking the same mass but moving it farther away made it harder to rotate. What if, on the other hand, I put the mass like right here? Did it get easier or harder? I think it's going to be really easy, right? Because now just by grabbing this, I'm almost grabbing the mass itself. It's just like, hey, let's turn it, right? Big deal, okay? Same mass in all cases, but the distance from the rotation axis affects how much opposition it puts up, okay? And the equation looks like this. It's equal to the amount of mass times its distance from the axis of rotation squared. So that distance from the axis has more of an impact than the mass itself. Where it's located has much more impact because it's squared than how much mass you have on the end of that axis, okay, or on the end of that rod. Here's the thing. This is one equation for moment of inertia. This equation is only for this. It only applies to this one particular case. However, we can say that all other moment of inertia equations are built from this one. It sort of holds the overall principle of moment of inertia. More mass, harder to rotate. Distance from axis of rotation affects how much harder it is to rotate, okay? Everything is built inside of this equation, and let me show you how. So let's like expand what we just did and say instead of one point mass, what about many point masses? So maybe again we have an axis of rotation, and I'm going to connect one mass here. Let's call that M1, and it's a distance of R1 away. And let's put one maybe like right here, relatively close but smaller. It's a distance R2 away. And then maybe one like way over here somewhere, and let's say that it's a larger mass. Maybe this is M3, and it's R3 away. You might be starting to guess, like, well, if everything is built on this equation, and I know how we did this for one point mass, I bet it's not going to be terribly different for that. It turns out each one of them has exactly the same equation impact on how hard it is to rotate. And you can almost imagine, like, I could tweak how hard this is to rotate by like moving the different masses in closer or out further, and I could get exactly the amount of opposition that I want. And it turns out the equation looks exactly like what you might expect. I, in this case, is going to be M1 R1 squared plus M2 R2 squared plus M3 R3 squared, and that would continue for as many as I may happen to have. Each one of them has the same type contribution to the moment of inertia, depending on how far away it is and how much mass it has. You get the idea so far. If you're thinking, like, where's he going with this? Just give me a second. You get the idea of moment of inertia. Opposition to being rotated, and it's dependent on where the mass is located from the thing you're trying to rotate it around. Is it close or is it far away? All right? What if we take this same idea but go a little crazy with it? Let's keep an axis of rotation here. And now I'm going to put a mass a distance r away. And let's say we have, a bunch of these the exact same distance away. So maybe one there. I don't know if I can make all these r's the same distance, but hopefully you can get the idea. And we'll put a mass here, and a mass here, and a mass here. But let's keep going. Let's put one right out here, the same distance away. But then let's keep going, and let's put one like right next to this one. But then let's keep going to infinity, okay? Such that maybe I've got like essentially an infinite number of these masses all so close together I can't even really tell they're separate, such that it forms a circle, okay? So you ready for terrible? This is going to be terrible. Circles. Ooh, that could have been worse. And let's go to this outer one. I shouldn't have gone around the opposite direction. Oh, you get the idea. And imagine that this circle is formed of just an infinite number of little pieces of mass that are all the exact same distance away from the middle. Essentially what I've done is just made, well, like a ring or a donut. A sad donut. A donut that's mostly whole. That's just depressing. I don't want that donut. Oh, who am I kidding? I'd still take it. A donut's a donut, right? Even a bad donut's better than no donut. Is that true? Yeah, I think it is. Yep. Unless it's a rotten donut. Then no donut is better. But as long as it's edible and somewhat tasty. Anyway, enough about donuts. What are we going to say about this particular case? You might imagine that it's the same idea. It's M1 R1 squared plus M2 R2 squared plus blah to infinity. Because I can't even really tell how many of them I have. Okay? But keep in mind, in this particular case, well, all of these R's are the same. So let's factor out the R. And then I've got M1 plus M2 plus M3 to infinity, which is really just all of the mass, the total amount of mass that forms that ring. Okay, so let's say this is a ring or donut. Notice I ended up with the exact same equation, right? Except now, instead of a point mass, it's just all of this mass for the entire thing times that constant distance it is from the axis of rotation. Okay? You're thinking, like, how many times are you going to do this and get essentially the exact same equation? I'm done. Because we're going to change it a little bit now. All right? What if we took this donut? And I want to use donut instead of ring because it's easier to imagine what I'm about to do. And let's say we took like a rolling pin, you know, if any of you bake, like we want to take the donut, we're going to make it flat. So I'm going to take the donut and just smash it in toward the middle from all directions. We're going to turn the donut into a pancake, a donut pancake. Boy, that sounds tasty all of a sudden. I just opened a new bakery, right? All we're going to do is make donuts. We're going to turn them into pancakes, give you a stack of donut pancakes, syrup over the top, bacon on the side. That might work. No? You don't think so? No. There's been weirder things in this city, I'm pretty sure, right? Donut pancakes. So we're going to take the mass and smash it toward the middle so that this doesn't really change in the sense that the radius is still the same, but now it's like solid, okay? So same R, same M total. It's just it's in different places now, right? Things have changed. Some of the mass is now really, really close to the center. Some of the mass is still all the way on the edge. Some of the mass is halfway. Some of the mass is a little bit away from the middle, okay? It's almost like we took this with all of its little rods going out and we put them at all sorts of different locations. So R is like all the possible R values, and M, well, all the little pieces are still the same and they add up to the same total mass, but a lot of it is now closer to the middle. Did this get easier or harder to rotate? Remember the concept. Farther away or more of it makes it harder to rotate. What can we say about, on average, what's happened to this mass? It's gotten easier because a lot of it's gotten closer to the middle, okay? This is easier to rotate. This has a lower moment of inertia. So lower I, because R is, we'll say, less for many parts of the mass, okay? The overall size of it hasn't changed, but for many of these little pieces of mass, they are now closer to the center, closer to the axis of rotation. And if you think about the way I described that, we're not going to do this in this class, but what I want to do is still that same equation, M1 times R1 squared, for every little piece of mass that's in here, all with the same M, but every one having different R's. And I want to add all of those up to infinity. Well, that's just another way of describing integration. We're not going to do those integrals in this class, okay? So the way to get to this is from integration. And you will get, for this particular case, 1/2 M total times R squared. I will leave it up to you if you want to play with that. You're not going to be required to do any of that in this class. If you are a physics major or want to become one, there will be a class at some point down the way where you'll have to do such things, okay? But don't worry. It turns out someone has done all the work. Ooh. Okay? So for common symmetrical geometric shapes of things that may be turning or rotating, someone did the calculations to try to figure out exactly what the moment of inertia is for them. So here we've got a sphere that's solid. It's got mass all the way through. Here it's empty in the middle. Here we've got essentially what we just did, right? The hoop versus, or the ring versus a solid disk. You can say this one's mr squared, that one's 1/2 mr squared, and a bunch of other shapes rotating around different axes, okay? Your job will be in the problem, a thing is rotating, recognize what the object is, so you know which equation for I to use, okay? You should also be able to be given like just random things, and based on whether the mass is closer or farther apart, be able to say, I think that one's got a higher I, or that one's got a lower I. You should know the principle in general, okay? The principle in general goes back to that equation, okay? Who's got questions? Who's got thoughts? Who wants donuts? Yes, I'm with you. I want donuts badly now, but alas, that's not going to happen for a while. Yes.
So for that solid sphere where you have 7 fifths squared,
Yeah.
that would be harder to rotate because
It's harder to rotate because notice they've moved the axis to a weird place, so it's not just a sphere that's spinning around an axis through its middle. It's more like we took the sphere and now the whole sphere is like moving around this axis. More of its mass is farther from the axis of rotation. So you end up with a bigger value. Okay? So what are we going to do with all of this? Let me show you. First of all, let's see if you understand. Notice 2 spheres, same radius, same mass. Same radius, same mass. One is solid, one is hollow. They're using different metals so you can actually have it be hollow but be the same mass, okay? One is solid, one is hollow. Which one has a bigger moment of inertia? Which one has more of its mass farther away from the axis? The hollow one. The hollow one has a larger moment of inertia. Okay, the other one is kind of like a 3-dimensional version of the donut that we smushed toward the middle and turned into a pancake. Okay, it's the same idea, just more of it closer to the middle. Which means, as we go further here, this we're not going to do. Ta-da! This next one talks about actually doing the integration. We're not going to do that. Aren't you glad that we had days full of smoke? Maybe. I don't know. It got you out of integration. So there you go. Congratulations. Which brings us to this, and this will be the last slide that we do today, and we'll do the example problem connected with it on Thursday. And that is what we're going to do with all this information. Okay? We're going to deal with things that can roll. Now, all those problems we had where you had like an incline with a box that just sort of slid down, right? Now we can do something like take a ball and let it roll down the slope. That's a little closer to the real world and incorporates more possibilities that you could encounter calculations for. So in the case of something that's rolling, it has 2 types of motion. It's rotating and it's moving from one place to another, much like the yo-yo. It was rotating and it was moving, okay? We are going to deal with a very specific type of this case, which is called rolling without slipping. And I should have put that point first. First of all, what is rolling without slipping? Have you been bowling? Boy, this is just old-fashioned day, right? Yo-yos and bowling. I don't know. So if you've been bowling, like someone who's made, the bowling ball is heavy. So someone who's stronger, right, you can imagine they're like, I'm going to knock all the pins down, and they're like, you know, like that. And what happens with the ball? Like it flies through the air a little bit, and you're like next to these people that are doing this, and it goes bang and hits the wooden floor, and you're like, they're going to break things, and then it like bounces into the other lanes. Everything is terrible. No. So let's say they manage to keep it going straight. It flies through the air, and then maybe it hits, and it's going so fast, it doesn't even have an opportunity to spin yet. It just like starts sliding, and then eventually as it loses a little bit of speed, like it starts to rotate and still slide, and then as it gets closer to the end, like it's spinning really fast, and then it hits, and it's like, whoosh, and everything is happy, or something, okay? In that particular case, that is rolling with slipping. It's rolling, but it's also like sliding along the floor at the same time. On the other hand, let's say you're a small child, or maybe some of us, okay? And you're like, heavy bowling ball, right? And so you just say, okay, fine, I'm just gonna set it on the ground here and just give it a little push, right? And you push it, and it never has a chance to do this sliding. Like as soon as I push it, it like starts rolling, and for every little bit it rolls, it moves that exact arc length forward, okay? There's no slipping, there's no sliding. That is rolling without slipping, okay? And you can imagine like, it's kind of the 9 seconds of yo-yo. You stand there and you wait and you're like, good job, little child, you pushed the ball. Yay, it's gonna get to the end. Yay, you did great. Yay! And then it gets to the end and the pins are like, did you feel something? Like we should, oh, it's a kid, fall over. And then a couple of them fall over just to be polite because they heard all the cheering, right? So that's rolling without slipping versus rolling with slipping. We're not gonna do the first case, it's complicated. We are going to do the second case where it's rolling without slipping. Keep that example in your head because I'm going to connect it to this first point on Thursday, and then we're going to work a problem that deals with that, okay? So, I will see you all on Thursday. In 47 hours, start your countdown timer of excitement, which I know you all have on your phone, right? It's like, ooh, next physics class in 47 hours, or 46, 45. I don't have one of those. No, I wouldn't do that. Goodbye. Farewell.
Yeah, 'cause like,